Alright, we are going to go through reaction kinetics in class exercise 2. Okay, so in this particular in class exercise, you are given a table with some changing conditions, and you're supposed to deduce the order of reaction with respect to each of the reactants from the information given. Okay, so right, so there are two methods which you should be quite familiar with after reading through your notes. The first method is by inspection. Okay, so I'm going to just illustrate to you very simply how we can do that by inspection. Okay, so the first thing is let us just check what are the reactants being made constant or being kept constant between experiments. So if we look at experiment 1 and 2, you realize that the initial partial pressure of NO is being kept constant at 0.40, whereas for the initial partial pressure of O2, it doubles from 0.60 to 1.20. You realize that the initial rate of formation of NO2 actually doubles from 1.2 to 2.4. Okay, so from here it is very clear that this is a direct proportional relationship. So therefore we can say that as the initial partial pressure of O2 doubles from 0.6 to 1.20 atmosphere, while keeping the initial partial pressure of NO constant at 0.40 atmosphere, the initial rate of formation of NO2 doubles from 1.2 to 2.4. So therefore the order of reaction with respect to O2 is 1. Yeah, so you can do it by inspection in this manner. Okay, so but if you don't really like to do it by inspection because it involves writing quite a bit of stuff, you can always do it by the analytical method, or otherwise known as the mathematical method. So what we can do is first we'll let the rate equations be rates equals to K partial pressure of O2 to the power M, partial pressure of NO to the power N. Okay, then after that, we'll compare between experiments 1 and 2, and what we're gonna get is we'll just divide by the initial rates of formation. So experiment 2 divided by experiment 1, so we're going to get 2.4 divided by 1.2, and then equals to this is K, and then 1.20 to the power M and 0.40 to the power N. Okay, then K 0.60 to the power M and 0.40 to the power N. Okay, and then we'll just cancel off the constants from the numerator and the denominator, and then we'll get 2 here, and then after that we get 2 equals to 2 to the power M, so therefore M is equals to 1. Okay, so this is how we can do it by the analytical method. You don't really need to explain, you just need to solve the mathematics. Okay, so for those of you who feels that you prefer to do it without writing much words, then I think the analytical method works for you. Okay, but for those of you who are you feel quite confident about your language ability, then by all means you can do the inspection method. Okay, however, the inspection method will be more difficult if you try to get the order of reaction with respect to NO in the case of this particular question, because you notice that for experiment 3, right, when you double the initial partial pressure of NO from 0.4 to 0.8, you also realize that the partial pressure of O2 doubles. Do you notice that? Yeah, so so normally in tutorials or in the lecture notes, when we give you a very simple scenario, right, we try to keep some parameters constant between experiments, but in our case here, experiment 3, both partial pressure of O2 and partial pressure of NO changed. However, you can still do it by the inspection method if you are, confident of a language. Okay, because in our case here, you realize that both the initial partial pressure of NO and O2 doubles. Okay, and then the initial rates of formation of NO2 increases by 8 times. Okay, so of course, if you are going to do it by the inspection method, you realize that when you write out, trying to explain, right, you'll be quite long because you need to explain to the reader, right, what you're trying to say. Okay, so for example, in this case, right, what you could say is that, oh, okay, so from the above working, you are aware that the order of reaction with respect to oxygen is 1. Okay, so therefore, when you double the initial partial pressure of O2 from 1.20 to 2.40, you if the order of reaction with respect to NO is 0, you expect the initial rate of formation of NO2 to double from 2.4 to 4.8. Okay, so I think you need to bring the 4.8 in. Okay, however, that is not the case because the initial rates of formation of NO2 actually increases to 19.2. Yeah, so if you look at 4.8 and 19.2, that is an increase by 4 times. Yeah, and then over here you notice that, oh, the initial partial pressure of NO also doubles. Yeah, so in this case, this increase by 4 times, or this quadrupling effect, right, must be due to the fact that you increase the initial partial pressure of NO by 2 times. Yeah, so from here, you can conclude that this is an example of a second order kinetics. So therefore, second order with respect to NO. Yeah, so, but you notice that a lot of things has been said. Yeah, so it's actually a little bit complicated here. Yeah, so my suggestion is, if you don't want to write so much, then I think doing by the mathematical method still makes a lot more sense, because if you do it by the mathematical method, then you have a lot less to write. So in this case, you are simply comparing between experiment 2 and 3. Okay, and then what you're going to do here is simply just put 19.2 divide by 2.4, and then you write out the rest of the parameters. So this is just k, and then 2.40 to the power 1, and then 0.80 to the power n, and then k 1.20 to the power 1, and then 0.40 to the power n. Okay, so if you do a quick cancellation, so you get 8 here, which is equals to 2 multiplied by 2 to the power n. So you just cancel. This is 4, which is equals to 2 squared, and this is 2n. So therefore, n is equals to 2. Yeah, so you can easily solve it by the inspection method. You don't really need to write much, so it's really suited for those of you who, like, you're just afraid that the more you write, the more mistakes you make. Okay, then next such question is usually followed by asking you to write out the rate equation in terms of partial pressure of the reactants. You notice that they are very clear what they want you to write the rate equation in, okay, in terms of partial pressure. So if you write in terms of concentration, you'll be marked down. So in this case, rate is equals to K, partial pressure of O to the power 1, partial pressure of NO to the power of 2. Okay, that's about it. Hence, calculate the value of rate constant, stating its units. So you can simply use any of the 3 experiments. So let's say we use experiment 1. So in this case, the rate is 1.2 equals to K, partial pressure of O2 is 0. Let's do a check, 0.60 to the power 1, and then 0.40 to the power 2. And then you solve for K, you should be able to get 12.5. Quickly, the units will be per atmosphere per second. Yeah, for those of you who are not so sure how to get the units, so let me just illustrate one more time. So in this case, let's check out the units for the initial rate of formation is atmosphere per second. Okay, so in this case it's atmosphere per second, and then we have 3 partial pressure here, so that will be atmosphere to the power of 3. Okay, so you bring atmosphere to the power of 3 to the left, you cancel, you get atmosphere to the power of -2. Okay, so that's how you get your units. Alright, so next we're going to move on to question 2. So for question 2, right, we have vanadium ions in 1 mole per dm cube of H2SO4 oxidizes arsenic 3 oxide to arsenic 5 oxide according to the given unbalanced equation. Okay, then you notice that there are 2 sets of experiments being performed. Take note that for both experiment, arsenic 3 oxide concentration 0.10 for experiment 1, concentration 0.05 for experiment 2, right? They are more than 10 times greater in excess in terms of concentration as compared to that of vanadium 5 oxides. And I guess most of you should be quite experienced with kinetics now. You know that they are doing that because they want the whole system to be pseudo nth order with respect to VO2 plus. So in this case, when you write out the rate equation, you'll be rate is equals to K concentration of As2O3 to the power of M and concentration of VO2 plus to the power of N. And because the concentration of As2O3 is way greater than that of VO2 plus, so therefore the pseudo nth order reaction is now rate is equals to K prime VO2 plus to the power of N. Okay, K prime here, right, is actually equals to the actual rate constant multiplied by arsenic 3 oxide raised to the power of M. K prime is what we call the experimental rate constant. Yeah, so that means that for this experiment itself, right, it is impossible for you to determine the order of reaction with respect to As2O3 for one experiment. Yeah, the reason is because the change in its concentration will be too negligible as the reaction proceeds. Yeah, and that is also the reason why we choose to do it having, in this case, because there are two reactants, if you want to measure VO2 plus, we will want arsenic 3 to be in excess. If we want to measure arsenic 3, let's say, then we will keep VO2 plus in excess. But in this case, we don't really need to do it because the reagent in excess, we can simply just double the concentration from 0.05 to 0.10 and we see how the curve changed. Okay, so we're going to look at the curve below. So, yep, the curve has been plotted for you. I think the graph looks a bit different from what you have in your in-class exercise because I think some of the minor grids are missing. So I think this graph is a little bit clearer. So now, yeah, so these are the two graphs you're going to get. Okay, so if we look at the question, you are asked to use the graph to determine the order of reaction with respect to vanadium 5 and arsenic 3 and then show your working clearly. Okay, you can use either of the graph to help you, but of course, whatever the case is, we'll try to look at an experiment where the decrease is greater. Okay, so in this case, like for example, experiment 1, it goes from 0.05 all the way to close to 0.015. Okay, so that we can at least check whether the half-life is a constant. Yeah, so in this case, if we were to check experiment 1, let's check it out very closely, right? From 0.005 to 0.0025, let's try to check. Okay, it's over here. Okay, yep. So this point would be let's see, 48 and 0.0025. Okay, in this case, we should be able to check out consecutive half-life. So we'll check from 0.0025 to 0.00125. No, we can't. It seems that the graph did not extend long enough, but it's fine. We can use other points to check. Okay, so in this case, let's see, let's check out where is a good point to check. Okay, maybe we can check 0.040, so maybe this point. Yep, so we'll check this point, so that's 15, so that's 15 and 0.0040, and then we'll check out 0.002, so that's over here. Yep, so that's 64, 0.0020. Okay, so we'll take 64 minus 15 for one of the half-life. Let me just punch the calculator. 64 minus 15, that's 49. Okay, and then we have from 0.005 to 0.025, that's 48. So the half-life is approximately constant at about 48.5 minutes. So in this case, we are looking at the first order kinetics. Okay, we are looking at first order kinetics when we are looking at, for experiment 1, first order kinetics. Yeah. So in this case, because the concentration of vanadium 5 is the one that decreases down, and it shows first order kinetics. So from here, we can conclude that for vanadium 5, it demonstrates first order kinetics, and the reason is because T half is relatively constant at about 48.5 minutes. Yep. Okay. And then the next part, you are asked to show the order direction respect to AS203. Okay, so what shall we do with AS203? So in this case, the simplest way is actually to draw a tangent. Okay, to draw a tangent at time equal to 0. So we are trying to find out the initial rates, okay, for the decrease in concentration of VO2 plus. Some of the students actually highlighted that, hey, like from the data on the graph, right, they can easily tell that the order direction with respect to AS203 is actually 1. How did they do that? Okay, so what they did was they simply look at the time. So 45 minutes, vanadium 5 is 0.026. But to reach 0.0026 for experiment 2, right, I need 90 minutes. So I need double the time. So because I need double the time, and the concentration of AS203 is half, so therefore I expect the order direction with respect to AS203 is 1. Okay, so some of the students actually use this as a form of argument. However, right, this is a very good way to do approximation, meaning that you already know that the order direction with respect to AS203 is likely to be 1. Okay, but you cannot use this as an explanation for this question. The reason is because the graphs are being plotted. So you cannot use the experimental data point as a form of argument. Yeah, so you still need to work on your graph. So in this case, you still need to draw the tangent at for experiment 1. Okay, so I can't exactly draw the tangent using the stylus, but yeah, so if you roughly get what I'm trying to say, so you have to draw this tangent, and then you have to draw the other tangents. Okay, and then of course in that case you can then compare the two lah. Yeah, so when you compare the two, then you realize that as one of the slope is steeper than the other. So in this case, experiment 1 slope is about double that of experiment 2. Okay, so if you do a quick calculation, you should be able to obtain that, and with that you should be able to conclude that the order of reaction with respect to AS203 is also 1. Okay, so first order. Then of course the reasoning is that the slope for experiment 1 is twice as steep as that of experiment 2, or you can say the gradient is double that of experiment 2, so therefore the initial rate doubles as the concentration of arsenic 3 oxide doubles from 0.005 to sorry, is it 0.05? Yeah, doubles from 0.005 to 0.10. Okay, so that's how you can formulate your argument. All right, yep. Then the next part we're going to look at is okay, so we come to part B, hence give the rate equation for the reaction. So in this case it's clear cut, so therefore the rate equation should be rate equals to K concentration of AS203 to the power of 1, and then concentration of VO2 plus to the power of 1. Okay, Okay, so take note that I wrote 1 here is really for illustration purposes. So when you write out for exam, you don't need to put the 1s. Okay, it's really for teaching purposes. Okay, then finally, calculate the initial rate from experiment 1. Okay, and use it together with your rate equation to calculate the rate constant for the reaction, including the units. Okay, so you would have done this. Okay, you would have done this in your earlier parts. You would have done this for part A. Okay, when you actually measure the slope. Okay, so in this case, based on the teacher's reading, the initial rates for experiment 1 for the teacher's reading is found to be 6.8 times 10 to the power minus 5 moles per dm cube per minute. Okay, you will get a value that is quite close. Okay, it need not be exact. Okay, and then in this case, your rate constant will therefore be based on this. So you need to shift this portion over here. So will therefore be 6.8 times 10 to the power of minus 5 multiplied by the initial concentration of arsenic 3 oxide and then the initial concentration of vanadium 5. Okay, so both of these are to the power of 1, and then you end up with 0.136 per mole dm cube per minute. Okay, I don't think I need to show you how to derive this. Some students ask whether we can leave the answer as per second. So my suggestion is no, you don't have to change it to per second. You can just leave it as per minute because the question have time as per minute. Okay, so I hope that answers most of your queries. There's one final thing which I thought I should make a brief mention because some of the students might be thinking along certain direction. Okay, so as we have shown earlier on that this is a pseudo first order reaction, right? Okay, then you might be wondering, right? The T half being ln 2 over K, is it K or K prime? So obviously in our case here, it has to be K prime. It has to be K prime. Okay, there's no argument about it. It has to be K prime. Okay, so therefore this is K prime, then therefore your T half is actually equals to ln 2 over the actual K multiplied by AS2O3 to the power n. Okay, so of course in our case here, you notice that because the gradient, the slope of experiment 1 is double that of experiment 2, right? You know in this case that my n is actually first order. Okay, so in this case, you realize that the T half from the above experiment is inversely proportional to the concentration of AS2O3 because ln 2 is a constant and K is a constant. So it's an inverse proportional relationship, right? So therefore, some of the students might be wondering, can I use the T half as an argument to prove that it's actually first order kinetics for AS2O3? Okay, you can use T half as an argument if experiment 2, right, is being conducted beyond 90 minutes. So let's say they conduct to about 120 minutes. Because for experiment 2, if I extrapolate the line, right, okay, I mean my extrapolation isn't done so well, so I extrapolate a bit. Okay, sorry, a bit, right? So you realize that about 0.025, right, about here, right? So I mean for the VO2 plus concentration, when I halve it from 0.05 to about 0.0025, right? The time is about 96 minutes there about. So you realize that the original T half is about 48 minutes, right? So your T half really doubles from 48 to about 96, 95. Yeah, so you can use this as an argument for first order kinetics because the T half actually doubles. However, in our current scenario, you cannot use it because you're not supposed to extrapolate the line on your own outside the graph paper. Okay, anyway, even if there are ample rooms in the graph paper, you're not supposed to extrapolate the lines. You are only supposed to work within the plotted lines. Okay, let me repeat. I think this also applies to your practical. You are supposed to work within the plotted lines, not outside the plotted lines. Yep. So because of that, then I'm sorry, in this case, you cannot use T half as an argument. So I think you have no choice but to use the initial rate method to help you to find out the order of reaction with respect to AS load 3. Okay, so with this, I hope you find the debrief useful. So do keep a lookout for in-class exercise 3 next.